We are rolling. All right. So, why call it tangent? So, on your calculators, who brought the calculators with them today? Who brought their calculators with them? Remember, bring your calculator every day. It doesn't matter as much for guys and gals that are seniors, like Mr. Legscheider here, but it matters for Mr. McAlpine, who's not paying attention to me. It matters to Mr. Mangelson, who is a sophomore. It'll matter to him a lot next year. Why does it matter?
ACT.
Why do I want you to bring your calculators here? This is not the ACT. So I know how to use it. If I don't know how to use it and I bring it to the ACT, is the calculator going to help me as much as it otherwise could? No. Bring your calculators every day. It gives you the opportunity to practice on your calculator so that when you're in the ACT, you don't say to the proctor, I don't know how to use my calculator. And then the proctor goes, sorry, I can't help you because I don't know how to use your calculator either. Okay? So bring them every day. Okay? You should have a pencil. You should have your notebook. You should have a calculator. You should have those three things every day in class. Okay? Now, on your calculators, you'll notice a few buttons, a couple of them that we've covered. We covered the one that says sin on it. It'll say sin like that. So if you want to do something naughty, that's the button you push, right? Okay, it's a little trigonometry joke. You guys can laugh. Even if it's a polite laughter, Nick, you can laugh, right? Thank you. Thank you for the polite laughter. All right, and then there's the other one that's, you'll hear that say, they'll say cos a lot. Cos. Okay? We've gone over these. This one does sine. And this one does cosine. Okay? And there's a third one right next to those two, and it says tan. Who sees the tan button on their calculators? Those of you that have brought your calculators. Okay, we're going to talk about what that's about now. Okay? And we've already talked about it a little bit in geometry last year, have we not? All right, so let's talk about it some more. Let P be a point on the unit circle. What's the radius of my unit circle? What's the radius of my unit circle? 1, right? Why do I want it 1? My hypotenuse is 1. Why do I want it to be 1? Makes all my math easier. Makes all my math easier. Okay. Now let P be the point on that unit circle where the terminal ray intersects the unit circle after rotation of theta degrees as shown in the diagram below. So, everybody makes sense of the diagram, yes? Using triangle trigonometry, what are the values of x sub theta and y sub theta in terms of theta? We've gone over this too, right? Check this out. Let's assume this was 30 degrees. Let's assume theta, so let me write that down. I don't like the regular pen, I like the calligraphy pen. Assume theta equals 30 degrees. Now, not 30%. Guys, help me out. Help me out. 30 degrees. All right. Now, if I assume theta equals 30 degrees, what is the length of this side of the triangle? We'll do this side first. Refer back to your 30, 60, 90 triangle, right? You should go back to lesson 2 and look back to your 30, 60, 90 triangle. What's the length of this long side on the x-axis, Soren? Square root of 3 over 2. Now, if that length is square root of 3 over 2, then what is the x-coordinate of this point P? Nick. I'm not quite sure. I'm not quite sure I understand. So if this theta is 30 degrees, that's theta, right? And I'm just making an assumption, saying let's assume that that theta equals 30 degrees. Oh yeah, yeah. We never draw a scale in geometry because then I make assumptions that aren't necessarily true. So don't assume scale, okay? It's a good point though. Good point, Nick. Now, so this length is square root of 3 over 2. What about the length right? And I'll do this one in red. What about this length? What is that length? That's 1/2, right? Now, what is the sine of 30 degrees? It's this. It's opposite over hypotenuse, right? So it's 1/2 over 1, which equals 1/2. And what's the cosine of this angle? How do I find cosine? Adjacent over hypotenuse, which is this root 3 over 2, divided by 1, which is just root 3 over 2. Now, check this out. This point P. What are the coordinates of point P? I want numbers now. If I go root 3 over 2 to the right, and then if I go root 3 over 2 to the right, and I go 1/2 up, and I started from where? The origin, right? What are the coordinates of point P? Go ahead there, Zach. Root 3 over 2, comma, 1/2. And so, cosine of that angle is simply the x-coordinate. And actually, I want to do that in black. The cosine is the x-coordinate. The sine is the y-coordinate. Okay? So, what are the values of x theta? Now let's forget, now we're going to forget our assumption up here. We're going to forget that theta equals 30. Now, theta is unknown. And now, the point P is what? The x value is whatever the cosine is, and the y value is whatever the sine is. So the coordinates of point P, Kaya, is, well, if I don't know the angle though, if I don't know the angle, I just put it in terms of whatever the angle is that I don't know. So I put cosine theta for my x-coordinate, and for my y-coordinate, Brandon, sine theta. Okay, now, I don't know why they do this without telling you what tangent is, but let's call this review, shall we? Let's call this review. Using triangle trigonometry, what is the value of tangent theta in terms of x sub theta, y sub theta? They want you to be really good at saying, well, x sub theta is this, right? And y sub theta is this. So tangent of that angle, who remembers what tangent is? Go ahead, Sophie. Opposite over adjacent. So let's go back up to our original unit circle. If I got theta here, theta's right there, right? What is the opposite side of my angle theta? Is it the black or is it the red? It's the red, right? So my opposite is the red, which is my y, which is also sine. Okay? So tangent theta, it equals opposite over adjacent. And we understand that the opposite side in this triangle is sine of theta. We got that from our triangle up here in the unit circle, this guy, right? What's the adjacent side? Is it the red or is it the black? It's the black in here, right? It's this guy, which we figured out is also the cosine of that angle. So, tangent is simply, there are a couple different ways of looking at it. I can look at it as opposite over adjacent. I can look at it as sine theta over cosine theta. Or I can also look at it as, oh, there it is, right here, right? Sine is my y value, cosine's my x value. So I can put it also as y over x sub theta. Meaning, if I'm on the unit circle and I go up to a point on the unit circle, that point, the y divided by the x, is going to be the tangent of that angle. It's a lot to drink in right now. Okay? You just need multiple terms or multiple times going over this. All right? What is the value of tangent of theta in terms of theta? Well, we kind of did that already, didn't we? We already did that because we got it right here. My arrows are just awful. Okay, we'll do it the old-fashioned way. That's it in terms of theta. Okay? So on to the next page. Are you guys keeping up with me? Or am I going too fast? Keeping up? All right, good. If I'm going too fast, just throw something at me. Well, don't throw anything at me. Okay? So, now we're going to talk about, let theta be any real number. In the Cartesian plane, you know, who knows what the Cartesian plane is? Who knows what the XY coordinate plane is? Who knows what a graph is? Yeah. Who's just not paying attention? So, this is the XY coordinate plane, right? I got an x-axis and a y-axis. It is also called the Cartesian plane in honor of the guy who invented it. Who has heard of Rene Descartes? Who's ever heard of the phrase, I think, therefore I am?
Me.
Yeah. Right. That was Rene Descartes. He was a mathematician. He was a philosopher. He was also a mercenary. He was a bad dude. But he was a really good mathematician. He was the first one to come up with the graph, and what it did is it helped marry algebra to geometry. So never before Descartes did they relate algebra to geometry very well. And Descartes did that for us. That's why we call it the Cartesian plane. You'll hear me refer to it as that from now on. So anyhow, in the Cartesian plane, rotate the non-negative x-axis theta degrees about the origin. What it means is, pretend that you have an xy axis like that there, right? And then you're going to rotate that about. So now you got it like this. okay? And they want you to look at theta, okay? I don't know why they worded it like that, but okay. So I want to look at theta. Now the value of the tangent of theta is this y value, y sub theta, divided by x sub theta. And what's the other way of looking at it? Go back to your first page. If I look at it in terms of the coordinates of the points, I can do that. I can also look at it in terms of that angle theta. How do I represent it in terms of that angle theta? Sine divided by cosine. Okay? Now, why does it say this little part right here? Why does it say for cosine theta not equal to 0? Why do I have that? Why do I put that in there? Well, it can be less than 0. It can be not equal to 0 means it could be either greater than 0 or less than 0, but not equal to 0, right? Why can't it be 0? Why can't theta be equal to 0? What do you think, Zach? Yes, physically speaking. Geometrically speaking, yes. How about algebraically speaking? What happens to this equation when cosine theta equals 0? Can't divide by 0, right? So that's why they put it in there. Good thinking geometrically, Zach. Okay, now, next page. For each value of theta, use the given values of sine and cosine to approximate tangent theta to 2 decimal places. So how do you do that? And what do you punch in your calculator, Nick? Sine divided by cosine. So you take this guy and divide it by this guy. And then you get that guy. So make it so, number one. Fill in the table on the right to 2 decimal places. Let's get started there. I'm going to pause this. For it again. All right. Now, as theta approaches 90 degrees and negative 90 degrees, what does the value of sine theta approach? What does this guy approach? It gets closer and closer to 1, right? It gets closer and closer to 1. Now, as theta approaches negative 90 degrees and theta is greater than negative 90 degrees, what does cosine theta approach? What does cosine theta approach as I get closer and closer to 90 degrees? It's closer and closer to 0. 0. So, think about this. If I divide by a really small number, it's like multiplying by a really big number, right? Okay. So, as tangent approaches negative 90 degrees and theta is greater than negative 90 degrees, how would you describe the value of tangent? What did tangent do? It got bigger and bigger towards negative, right? It got bigger and bigger in the negative. It goes towards negative infinity. It goes to negative infinity. We haven't really talked about infinity yet. And we won't talk about it much here. We will get to talking about it in pre-calculus a little bit. And then you'll talk about it a lot in calculus. Why would you do that? You don't want to learn? You don't want to learn. Good luck with that. Good luck. Now, as theta approaches positive 90 degrees and theta remains less than 90 degrees, so that means we're down here, right? Our tangent shoots up to positive infinity. Our tangent shoots up to positive infinity. And then letter E asked, as theta approaches 90 degrees and theta is less than 90 degrees, what is cosine approach? We kind of done that already. Okay. Here's a question that we had trouble with last week in the problem set. What does that word that I underlined mean? Who remembers looking at that problem with the Ferris wheel? And he said, well, how do I answer this question? And it was a question that had two words in it that we were not familiar with. One was domain, and the other one was range. What was the range? Yeah, the y values that were possible, right? And on the Ferris wheel, there was a limited number of y's that were possible, right? Because it didn't get any lower than a certain point, and it also didn't get any higher than a certain point. The Ferris wheel don't go higher than the Ferris wheel goes. That's how Ferris wheels do, right? And the domain was, well, we looked at one full revolution, which went from 0 to 360. So the domains were all the possible x's. Now, when they're asking about the range of tangent, they're asking about all the possible y values. They're asking about all the possible results of tangent. And we saw something really big negative, and we saw something really big positive. It came from negative infinity and shot up to positive infinity. So, how will we describe the range of tangent? We call it all real numbers. Everything ranging from negative infinity all the way up to positive infinity. We say all real, girls, please, all real numbers. And there is a shortcut way to write this. So write all real numbers, just like that, and then in parentheses, I want you to do this. That is the symbol for all real numbers. Okay? A little set theory for you guys there. Did he want me to do this? I can't remember. There it is. Yep, we're going to do it. Oh, he didn't want me to do that. All right, so suppose the point P is on the unit circle attained by rotating the initial ray through 30 degrees. Find tangent of 30. How do I find tangent of 30? Lose the calculator. Do this algebraically. Tangent theta equals, how do I find theta or tangent in terms of theta? Before I go to the 1/2 divided by root 3 over 2 though, what functions am I using? Sine over cosine. Sine theta over cosine theta. All right? Now, if I want to find the tangent of 30 degrees, I simply take the sine of 30 degrees and divide it by the cosine of 30 degrees. This is my fun part, because we get to do fun with fractions Friday on a Wednesday. Now, what is the sine of theta? Or what's the sine of 30 degrees, I'm sorry? 1/2, good. And then I divide that by what? Root 3 over 2, good, Nick. Riddle me this, Batman. How do I divide a fraction by a fraction? You two are saying the same thing in different language. Yeah, so equals 1/2 times 2 over root 3. I take the reciprocal of my denominator, and then I multiply the 2. All right, how can I make my job easier? Before I do that, though, Caleb, I can make my job easier by canceling out the 2's. And then I got 1 over root 3. And then, Caleb, what did you say? Yeah, what do we call that process? Rationalizing. Rationalizing is trying to convince yourself that something you've done really stupid was actually quite smart, but it's also getting radicals out of the denominator. Don't ask me why. Anyhow. So I multiply both the top and the bottom by root 3. And then the top, 1 times root 3 is root 3. Root 3 times root 3 is 3. And there is the tangent of 30 degrees. Okay, good. Bam. Do I do that? I think we're done for the day. We are done for the day, ladies and gentlemen. How great was that?